test. Cool. And that looks like we're live. Nothing there at the moment. Cool. So today I want to look at the recursive length prefix encoding that Ethereum uses for everything. And I have been reading this document plus just Googling a couple others. I think I was putting it off a little bit. I mean, it was absolutely everywhere. But I think I was putting it off because I was like, oh, it's probably encoding is quite difficult. But it really isn't actually, which is quite nice. So, once I get this back up, what it essentially is instead of saving items, and I always look at it as like JSON, when you're writing stuff to files, I use JSON a lot just because it's readable and you can open it in Notepad or something and have a look at it. In some configurations you use TOML or something because it's, again, even easier to understand as a human. But when there's computers, you don't want that. And in certain situations, you want it a little bit more complicated if it saves you space. And that's exactly what this is doing. So essentially what it does is you can either have a byte array or a list of items. And what that pretty much means is if you've got a string or an integer or something, they are encoded as their normal encoding within everything. And then it gets encoded as a byte array within the program itself. RLP doesn't give a crap about how like the basic types are encoded. All it cares is that it gets a byte array or an array of byte arrays. So in these examples, they all just assume it's string with an ASCII encoding. And that just makes it easier for you to understand. And the benefit of this is it maintains that. So if you've got, a dog, and you're encoding that, the D, the O, and the G are still ASCII, and they're still going to be readable. They just chuck this byte in front of it, and it changes depending on the size. And they've pretty much made 1 byte go as far as possible, and it's just a descriptor of the data that's following it. So you can kind of see what it's saying here is dog is 3 bytes long, and the 080 is this, if it's a byte array, string byte array, that's less than 55 bytes. The first one will just be 080 plus the length of the string. So they got 080 plus 3 equals what gets chucked here. So they got 3 following it. That remains readable because the ASCII still stays the same, but you've got the size. So the first thing you read in when you've got an iterator is going to be what sort of data is there and how long it is. So you can literally just read this first one, figure out that it's a 3, and then just read the next 3 into whatever data structure you want, and you don't even have to look at it. And that's pretty much what the library I think we're going to look at today is going to have. Because it doesn't actually care. And to be honest, most of the stuff in Ethereum, go source, GitHub, Ethereum, Go-Ethereum, clear. How'd that work? CD, go, source, Ethereum. Tmux, CD, RLP. There's not even that much in here. So yeah, if it's a string that's less than 55 bytes, they'll manage to do it in one. If it's a list, they do the same thing, but they say it's a list, not a string. And then it's also got in it the size, which is this 8. So a string, yeah. If it's a list, less than 55 bytes, and at 55 bytes come up, it's a C0. So it's an 8-0 if it's a string, it's a C0 if it's a list, and then they add the length. So this has got 8 bytes in it, so it's the C0 plus 8. Then in each one is these string elements, also if they're prefixes. So the computer can just read, say I've got to read 8, reads all of them into the next one, recursively opens it again, 8, that's 3 length, read 3 into whatever it is, read 3 into whatever it is. And they got some stuff here for special characters and empty lists. So the integers is 0 and a null string. Yeah, that's actually probably all there is to it. But we'll go through and see what they've got. Vim encode test. Let's go test. So we'll just look at this test suite and see what they do with it. So they just go through the big integers and they say it should be whatever it is. Okay, that's unexciting. 0 should be 080. 1 should be 1. 127 should be 7F. 128 gets an extra. That's when you actually, because it's above 55 bytes, it'll get an extra byte put in front of it, which is this 81. So it's an 8, 0 plus a 1, then an 80. Same deal. What they end up doing is if it's bigger than 55 bytes, that first bit here that tells you how long it is actually becomes the bit that tells you how long the descriptor of the length is. So here 256 is 8 plus a 2, and that 2 no, that doesn't even refer to that at this point. This is 2 bytes. So it's 1, 2. 1024 has got 2 bytes as well, 0400. Jumped ahead. In the next cases, they start describing no, none of these do. But the next level is if it's greater than 55 bytes. And if it's greater than 55 bytes, the descriptor, I can't even see it here. This number here will tell you how long the size descriptor is, and that follows. I can't see it here at all. Yeah, so this one here. if it's bigger than 55 bytes, RLP will be B7 plus the length of bytes. So here it's B8, which means B7 plus 1. And that 1 is the length of the size, which is shown here. So 38 bytes, I imagine that's 38 letters, follows. So if it's less than 55 bytes, it's an 80 plus however long the string is. If it's longer than 55 bytes, it's B7 plus however long the size is, and in this case it's 1, and that gives you here how long the actual string is, which is 38 bytes. Lorem ipsum dolor blah. Cool. None of these show that at the moment. 8F. Output. Yeah, here it is. This is them testing the edge case. So lorem ipsum has B7, which is the largest here. The upper length of how long a 55 byte long. So this must be 55 bytes exactly. So that byte describes that it's a string, and it'll be 55 bytes long, and this is the ASCII of it. I wish I have an ASCII table. C. A, B, C, 4. 4C is L. For lorem, capital L. Nice. Whereas here, because it's got the extra byte, lit, instead of Eli, it's a B8, which is the first of the greater than 55. So this 38 is now the descriptor of how many bytes it is. And 38, 56 decimal. Then you got your 4C, which is your L. And your 74 is the last byte, which is T, little t. Bam. Makes sense. Then I got the big one. The proper one there. Cool. Then they got arrays and stuff. Cool. That's enough of that. I want to go for actual code. So let's just have a look at what's in here. Raw. I think they're just pre-computing a lot of stuff in here. Count values, read kind. Yeah. So you got a switch for 1, 2, 3, 4, 5, 6, 7, 8, 9. No, that's not what this is doing. Read size. String length byte. If s is less than 28 and b equals 0, return s nil. Read kind. So they got the buffer. Length of buffer equals 0, return 0. If the number is less than 80, then it's the actual byte itself. K equals byte. K equals kind. Tag size equals 0, content size equals 1. If it is less than that, then it is a string. Tag size equals 1. Content size equals that minus. So they do the 080 minus the B, which is whatever was in there. If it's less than that, then it's a string, but the size is a bit more complicated. They take the character after the first one. B being buffer 0, so the first byte in it. If it's less than 8, then it's a list. That's less than 55. If it's bigger than that, then you have to go through it individually. Reject values larger than the input slice. Cool. Read size. So all this does is it returns the size, and it's a byte. S equals that, case 1. Yeah, okay, cool. They do a switch on the length of the byte. So this is in bytes. So the size, when it's written here in bytes, and they're converting it to an integer that tells you how long it'll be. Count values counts the number of encoded values in B. For I equals 0, so it reads kind of B. So it's passed in a byte list, which is one of these with a list. I'll read the first one, read kind, which is this one below, and it returns the tag size. If it's a list, we give that tag size, and then it just increments their count and adjusts the byte now for what's remaining, and then it ticks through all of the whole length of it. Split list into a content list of any remaining bytes after the list. If k does not equal list. Okay, so the first line is they're doing split B, which I think is above. And bytes after value, which they do a read kind if it equals a list. Error. So I don't know why at this point raw value is a thing of its own. Vim doc. What's in doc? The package RLP purpose is to arbitrarily nest arrays of binary data. The main encoding method in Ethereum. Its encode structure, the specific atomic data types, strings, ints, floats, are left to higher order protocols. It must be represented in big endian form with no leading zeros. So we've got an encode, we've got a decode, we've got a type cache. I imagine encode's going to be what we want to look at. It's type cache though. Don't know, not interesting though, because we want to actually look at encode.go. How big is this? Huge. Encode is an interface, and it should just have a encode RLP. Encoder. Wow, they're putting a lot of comments in here. Let's exit that slide so we can read it a bit better. Writes the RLP of encoding a value to W. Small writes making W buffered. If the type implements the encoder interface, encode calls encode RLP. To encode a pointer, the value being pointed at is encoded. For nil pointers, EB, encode to bytes, encode to reader, encode buff, list head, encode. Put head, encode pull, reset, write, encode string header, encode string, list end, size to bytes to writer, encode reader, encode to reader. So they're going to quite a bit of effort to make it useful. Write unsigned integer, write raw value. Write boolean. So these are kind of like generic, we'll take any value. Write byte array, write bytes, write string, write encoder, write encoder no pointer, write interface, make size writer. So they're iterating, going through all the different types and just making it so. Put in writes I to the beginning of the B and in least order needed to represent I. In size. Cool. So if we go look at where were we? P2P. If we look at message. We've got encode to reader, encode to bytes. Content encoded, so reads a message from the reader and verifies its code. So the message equals read message, get the code. Content is here. Encode to bytes. So this is what gets called. And it takes an interface which is an interface 2. Blank interface. So this would be them initializing a blank buffer. Defer putting in it. I'm not sure what that means yet. I think I saw this encode buff pool below. EB reset. And then it calls EB encode val. Return EB dot 2 bytes. So what do we reckon? ENC buff pool. Where is that? Because they all do this get and put. Get. Okay, so it's just a sync pool. that returns a new so they're just giving some concurrency safeness around this encode buffer of size buff 9. So if we look for encode buff, first let's look at sync pool. They just give you locks and stuff over an await group pool. Set of temporary objects that may be individually saved and retrieved. Cache items. So when you're decoding lots of items or multiple threads, they don't want to be creating loads of these buffers because they just get left around and it blows out the memory really. So they have this pool which you can pull and take stuff off, but it doesn't actually get left behind when they close. So all they're doing is they're getting in a buffer, one of their special buffers, buff. Where's the struct for it? Encode buff. CD into RLP. Mac. Writer. It's all in encode. Get. Put. Okay. So the get, they got a pool of these buffers and it's just saying get me one. And then when it closes, put it back into the buffer. Which is just like a fancy way of saying new and close in relation to they've got a pool of these buffers for utilization when you've got multiple threads going. Still having trouble finding my enc buff. Here it is. So the buffer is just an array, byte array. It has headers, the list size and the size of the buffer. 9-byte auxiliary buffer for UENT encoding. So the string data, which has everything in it, where all the headers are, and the sum of all the sizes as an int. Cool. So encode to bytes is where we're looking at. they get one of these special pools. They call EB reset on it. Next. Which all it does is it sets, yeah, because they're passing around these things, they just need to check and make sure that it's all zeroed out. So I guess it's like when you start playing with threads, you need to make sure that everything's clean, because if not, these random buffers that you're making just get left around and bloat your memory. That's how you get these programs that take up like huge amounts of memory, because they're just not cleaning up this crap after they've made them. But it also means that they're not fully zero when you get them. So you're doing this, setting the header size to 0. If the string is nil, then you're setting the string to a nothing. Yeah, okay, cool. If it's not nil, so it's actually got something in it, you've got this new item from the pool and it's got information in it already. You want to make sure it's nothing, so you're only taking the first, no 0 elements. This means up to. So you go from 1 to 10. This means you take the first element to the 10th element. If you've got that, you're saying up to the 10th element. If you've got that, it means up to the 0 element, which is nothing. If the heads is not nil, you do the same thing. So all they do is they get this pool, which is this item here, is a set of temporary objects that may be saved and retrieved. Multiple Go routines can play with it. Its purpose to cache allocated but unused items for later use, relieving pressure on the garbage collector. Reused by concurrent independent. Cool. So you got this pool of these structures. And you get one off it, you make sure it's 0. What's in it again? String, list of headers. I'm not fully sure what they do yet. The size of all the list headers, and the size of all the stuff in it. Call reset, and then you call encode the value. And this is obviously the meat of it. And once you're done with it, you return it as 2 bytes. So this does nothing except get you a new thing, make sure it's 0, call encode and put it into this new one. Call val on EB. So what's encode then? Such an encode is not. Here we are. Writes the head to the given buffer. No, that's not it, because that's on the list head structure. We want it on the enc buff structure. Enc buff pool. Right encode here, this one. Which is quite small as well, actually. So reflect value of val just gives you what type this is. So because they've got an interface here, they're saying you can put anything in here. In dynamic languages like Ruby and Python, this is what they do anyway. But in statically typed languages such as Go, you're normally meant to say, I've got this value, which is a string, or this value, which is a byte, or this value, which is an integer. And that's all well and good until you got something like this, where you need to encode every single value, and you'd have to make like 30 or 40 functions that would go through every single one saying encode byte, encode integer, and you don't want that. So you want this one, and this reflect type of value of, I think actually just gives you the value. Value. Is a value type. Cached type info. Returns a value. Reflection interface. So I think if you passed here an integer with a value of 10, so an integer of 10, because you're not telling it here that you're taking an integer, it doesn't know. All it's got is a random byte array that it doesn't understand at this point. This reflect package allows you just to play and get it out. So I reckon this now has your byte of, sorry, your integer of 10 now in it, and this would be an integer type. But in your program, you don't know what that is at this point. You've just got this random value. So here they're getting the type, cached type info. So what does cached type info give you? And I imagine that's a lot of what's going on in this package is you're making sure that you can take every single item. Okay, so it's going to be in this type cache. What was it called? Cached type info. Here it is. Function. Takes a type and some blank tags. Type key, type and tags. So there's a type key which looks like this. And all that is a wrapper around this reflect.type. So that's going to say integer or string or something. Give me an example. No. Doesn't want to give me an example. Bugger. Cool. So you've called this from here. You've passed it your integer. And it's got the integer now here. And it is trying to figure out what it is. So you pass in this, which says integer, to this cached type info function. The first thing it does is it makes a new type key, which just wraps this reflect.type and goes to the type cache, which is an array. Which is an array of type infos. Go away. An array of these, but it takes a type key and it has a decoder in there. So you've got an integer, you'll look in here for integer and it'll give you the decoder for an integer and a writer for the integer. So I'm assuming somewhere is a big list of what they could possibly be. Nope. So that was wrong. Do we build this type cache somewhere? So this info now returns this. I don't know where they've built this type cache yet. But it's going to have a decoder and a writer in it for the integer. And I think that's what'll get passed back. So this is one big shared type cache between all the threads, so they have to put some mutex and locks onto it. Unlock it now. Cached type info for the type. So I think we might actually build at the same time. If it does not equal nil, you can return it. If it doesn't, cached type info 1. So at this point, say it's the first time it's ever done it, there's nothing in there. So it'll call cached type info 1, which is this one here. So they're now going to be building a cache. The key equals type key. Reflect the type. So that's doing the same thing as up here. They're rebuilding this type key thing here. They're looking again in a type cache. This is exactly the same. Cool. If the info equals, so this like here is exactly the same. If it does not equal nil. So I think they're doubling it. And it's saying here another Go routine got the write lock first. And that, I believe, means they've checked it twice. And if they get it the second time but not the first time, then another Go routine got the write lock first. But, you know, if it's not in the cache, we need to generate the info for this type. So put a dummy value into the cache before generating. So they've got the key already, and they make a new type info, which is just blank. If the dummy value, no, they remove it if this is nil. So gen type info is actually getting the info out of the type. So they got this cache, and this cache is going to be for all the items like integers, strings, whatever. There's going to be a function that can decode it, and there's going to be a function that can write it. And this cache is just kept and used by everyone, but it starts off as 0, so you have to build it up. And this is what's building it, and they're calling a blank new type info and putting it under that key. So we've got an integer just gone in, calling new type info, saving integer as this new type info. But it's blank at the moment. Then they're calling this generate type info with the type and the tags, and the tags is nil at this point. But if it gets an error, if error does not equal nil, then they have to delete that out of it because it didn't actually fulfill. Then they save info into key. They're doing pointer arithmetic here, so that not pointer arithmetic. They're passing in the pointer so that the value is actually there instead of copying it. So it's all going to be in this generate type info. Info equals new type info, another blank one. This will be returned. Then they call make decoder, make writer. Make decoder. That's a bit scary. It's actually in the decode function. I guess make writer is in the encode function. Cool, so we go back into our other file, make writer, and it calls this. And what it does, I'm assuming, is it makes a writer. And it's a big list of switch case. Type.kind. There it is, there's kind. It's the type that it can be. Iota increments. So iota starts at 0. You go 0, 1, 2, 3, 4, 5, 6. So 0 is invalid. Bool, integer, integer 8. For all the possible things. So, now we're looking at it. If type equals raw value type, right? Raw value type. Interface, right big pointer. If it is a unsigned integer, the kind is an unsigned integer, return right uint. So here it literally just goes through every possible thing you can work with. And I'm assuming there's a heap more functions here. So we go if it's got a right interface. Where's the bytes? If it is a reflect.string, reflect boolean, we do write bool, write string, write bytes. Let's have a look at string. So write string. And here's a function here. Call value.string on value. No, that's a function. So what's actually happening is this return this function returns a writer. and an error. So the write string is a function that is a writer. And up the top, there was a interface that says writer, I believe. Maybe. So if it returns this function, which is a write string. So we've got a string. Now let's go back to integer. If it was an integer, an unsigned integer in this case, it'll return this write uint. It doesn't call the brackets here, so it's returning the function itself, not the actual result of the function. So this type cache, called this make writer, said integer. It's returned the write integer function here, which is now being saved in info. I'm assuming decoder does the same. If we go in decoder, and I reckon, yeah, they've done the exact same switch here. But instead of it being, if it is uint kind, decode uint. And it is takes a stream, writes it to the buffer. Cool. So what does that mean? So we're back in our encode. Encode to bytes. So it's encode value. Here. So they're encoding it. They're getting the value. They're getting the cached type info, which is returning this info structure that has a writer and a reader function. And then they're literally just calling this ti writer with the value. So this ti writer, when it was uint, was write how far out uint was this function. This function got passed to that cache. This type cache also saved it. Should I follow on here? What goes on here? Yeah. Writes it to info, returns info. Cache type info, saves the key. If it got an error, it deletes it out. So we now call in this write unsigned integer function. And they've got the buffer. So I equals value of uint. W.string. So they actually write in it to this string. They're appending 80 to it, which is that first one. If the value is less than 128, it fits a single byte. So they just chuck it straight in there. If it's more than 128, they have to get the size. Put int. I reckon it's put into something we'll have to look into. But they got the size buffer. They're just chucking it straight into it. Whatever's returned by is put int. I guess it's the size. S for size. And then they're changing the 0 to be 80 plus the size. So if it was an integer that was 3 bytes long, they put it straight into there, and then the size comes back here, it says 3, and then they change 0 to it. Oh no, sorry, this is an if. So it's if it's 0, they append just straight on that. If it's less than that, they just chuck it straight into the first one. If it's more than that, they chuck it into the second onwards, and then they write the size to the first. Append W string with the W size buffer. S+1. So what is this? Put int then. Writes I to the beginning of B in big endian byte order. Ah, this is that. Yeah, okay, cool. And it returns the size, yeah. So you got the integer, you got a byte, you've got to put it in. If I is less than 1.8, 1, 2, 3, 4, 5, 6, 7, 8. If 1 is less than that, that's in hex. So it's less than 256. It will just put the byte of the integer into 0. If it's less than 16, 8, 9, 10, 11, 12, 13, 14, 15, 16. If it's less than that number, they'll put the byte into the first one, I less 8. Oh, they're saving it as big endian. So when you're writing data to memory, endianness. Give me a picture. Yeah, the memory's going down. You've got an integer here, which is like 4 bytes. And you can either put it 0A, 0B, 0C, 0D, so going that way. Or you can do it the other way, which is DCBA. Which when you're writing like letters, it's almost always you're doing it like actually I've got a text editor here, don't I? So if you're writing a number, you got 1, 2, 3, 4, 5. That's almost the natural way humans write it. But the way the computers kind of like it is more like this. Because the computer reads the first one, puts it onto the stack. Then it reads the next one, puts it on the stack. Reads the next one, puts it on the stack. And then you've got them in order from top to bottom. And when you're doing calculations. And it's less calculations and more the fact that a computer CPU can only do 32 or 64 bytes at a time. And if you've got bigger numbers than that, then when they're doing calculations with them, they have to work from what is going to be the smallest part of the number first. And it's like when you do addition and you've got 6, 7, 8, 9, 10. You start on the right. You go 1 plus 1 equals 2. You put a 2 there, and then you go here, and you go, oh, that's 1. And it's a lot easier to write this in a bit of paper, but then that's got to carry the one here. So it's like the computer has to do that with everything, including strings. So we read it left to right, but it likes it the other way around because it wants to go right to left from the smallest to the largest. And that's called little endianness. And that means they write it like this. So you got an integer that goes A, B, C, D, and they chuck it the other way. So little endian here. And little endian is most computers these days. Yeah, I can't see where we're saying any, but yeah, little endian reverses the order. So the computers will always, not always, but Intels and AMDs want it in this little endian format. So it's just reversing everything. So what it's saying is, if it's less than 1 byte, it chucks it in there. If it's 2 bytes, then it chucks the first half in the first bit, second one in the second one, which makes sense until you got it left to right. So anyway, that's all it's doing, writing it as a specific encoding big endian order. I could go through endianness, but it always just confuses the hell out of me, and unless you're actually working in really low level assembly, it probably doesn't matter too much. So they're just writing it. So this encode, write uint, to do write int to w string directly. Encode integer to w string directly. Is that not what it's doing here? Put integer. I think they want to merge that one because it's cool. So they've got the encode, the make writer, where's the to writer to bytes? So back up. Encode string header here. And then they just write it, which is literally just returning a byte array to this rval, no, to the w, which is the actual buffer itself. And in the buffer there's this string, which is what gets returned. And when it's done, it returns an error, which should just be nil. Once it does that, I think it just, the 2 bytes, yeah, calls the encoding. This now buffer pool has the actual encoding in eb.string. And now they're saying eb.2bytes, and all that's going to do is return it. So here it is. Output equals a buffer of the size. Make a buffer that's exactly the size of it, and they save the size in there. So now they're going through that L heads, which I don't fully understand yet. So what is L heads? The header, the string data before the header. pos equals 0. They're calling encode again here on the header. Oh, because that header buffer had a different encode, didn't it? Which you haven't really looked at yet. So they're copying string position head dot offset. So you got your string at the position string pos, which starts off at 0, to header dot offset. And head is when they loop in through this L heads. And they're copying it into this output buffer. And then that returns the number of bytes, the position plus equals bytes. String position plus equals n. And then they write the header before it. That's what they mean, write the string data before it. And I feel like this is a super roundabout way of just copying exactly what's in this string. Oh, excuse me. Because the header actually hasn't been encoded yet. So, they've gone through and they've encoded, if you got a string, it's just 83 dog. The 80 plus 3 for the length, then dog. They've got that, and that's fine. And they've done that maybe multiple times in their thing. But they don't have this yet. The encoding for the header, which is just the list. So they've written all this, and that's all saved, and that's in the string already. So they're writing all that, that's fine. But they know they've got to have at the start, for every header, list header, they need to write what will be C8. So they write the string because they've got it, incrementing the positions and stuff. Then they go head.encode. And in our example, we didn't have a header yet, but if it was, I'm assuming there's an encode header. Yeah, that's too many heads. To writer, encode reader. And write uint, write bool, write integer, write no pointer, write big int, write byte array. Write string, write encoder. Write interface, slice writer. So if it was a slice, an array, they get the type info, the writer equals, yeah, okay. So this is the head and the tail. So they're going to recursively call type info, the writer equals function. So they've defined a function here. So they define a function and return the function, which is fine. That's what we were looking at before when it goes through the making a writer. So it just calls this. So if it gets an array, it'll call this. If it's Where's TS? TS.tail. Tags. The value length. Go through each item. They get the eType info writer. Val.index. So that's just really just going through every single element. So a slice has all the same type of element. That one, so they're getting the eType, so the element type, so what the elements is, and then it just goes through each element and calls the element type writer for and the writer function, I guess, takes an index. Val index. Index I, which is being incremented over. Cool. So it returns each element. So it still doesn't explain what's happening with these headers. Is byte, protective, raw, write bool, write that, write that. Slice writer, structure writer, pointer writer. Where do you reckon the header is? Where is it going to be writing this C8? I don't know. Inside. Right, byte array. Right, integers. This is the make writer. Encode reader. And then it's, I guess, a little bit different if they're writing to a reader instead of to bytes. Okay, buff pool. Put head. Yeah, here we go. List head. List head is a structure that has an offset and a size. The index is header in the string data. So this string offset would be at 0.0 or 0.1. That's what its offset is, and it's got a size. And that size is going to be 8. So it's going to put C plus 8. Encode. And it calls put head into the buffer C0 F7. F7 is the upper end of it, I guess. Yeah, that bottom to the alpha, I don't know what's doing that for yet. And the head.size. Head size returns a value if less than 56.1. If it's more, 1 plus integer size of size. Cool, boring. Put head writes a list or string header to buff. Buff must be at least 9 bytes long. Small tag, large tag. So we've got C0, F7. Small tag, large tag. If the size equals less than 56, we put in the small tag. Or no, that's saying if it's bigger than that, if it's 55 bytes. So if the size is less than 56, so it's 55 bytes, they'll put the small tag plus the byte size into buff 0 and return 1. Cool. So put head returns the size of the header, so if it's 1. Small size equals put integer 1 onwards size. Size. And it returns. So if it's 55 bytes or less, it puts the small tag plus that into 0. So this only puts the header, it doesn't actually put the thing in it. So it takes a buff. In the first position, it'll put the small tag, being OC0 for the list, plus the byte size in there, and return 1, saying it's 1. If not, size puts an integer of the size into 1. And then it puts a large tag plus the size of the size into buff 0. Size. Large tag plus the size of the size into buff 0. And then it returns the size plus 1. Because it's got the header as a 1 as well. So it's just put in the size and the large tag, which is this F7, and then you add to the F7. If it's a large index. And I don't think I really explained that before when I was going through it. So yeah, when you got a string, you got the size of the string added to this small tag. If it's bigger than 55 bytes, like here, in a string, it puts this extra tag here being the size of the string. The list does something similar. And I don't think they're going to have an example here. But if you've got a list, it says it's a list by this C0. And if that's as long as the list, which is all the elements of the list, including the headers, is less than 55 bytes, which is what they're talking about here, then it puts it all in here with a small tag here. So C0 plus 8 being 1, 2, 3, 4, 5, 6, 7, 8. Cat and dog is 6, plus 1 byte each for the header of both cat and dog. If instead of just cat and dog, it was more than 55 elements, say cat, dog, and this lorem ipsum elite, then the list does similar things by adding a length of the binary data. So it says list here, but it's got nothing in between it describing how long the list is, because it's encoded in here. If this was bigger than 55 bytes, they'd put another byte in here saying how long it is, and then this would be changed to show how long the size is, the size of the size, which is what they're talking about here. So they got this put head 2 bytes. So they've written the actual data here, and then they write their header, which is encode the head. Which is what we're just looking at then. Encode it, encode it, and I think if we go look at the decoder, list head encode just puts the buff, puts head. Cool, and that's it. And that's the full dive into encode. Yeah, and I think if we go look at decode, it's going to be very similar. I mean, it's a lot bigger, but the sizes mostly come because they're going through all the different types. So an integer is written as a, I think it's just ASCII data really. Everything up to this is exactly the same. They don't change it. They keep that so you can actually read it. The raw byte data. They're like, if it's a really small number, we don't want to change it. We just put 1 byte at the front. So decoding gives it an interface. Do I have an example of when we were in P2P? The server, Vim server, decode. Message decode. So in here, they got a payload come through called decode on the message, and makes a new stream. So I wonder what / new stream decode returns new stream. Creates a new decoding stream to read from. Byte reader interface stream will not induce any buffering. Optional input limit. So new stream. Type stream. Defining this stream a lot. Next. Stream can be used for piecemeal decoding of an input stream. It's useful if it's very large. And all it is a byte reader. With how many remaining bytes. And a additional metadata like size and what kind it is. Cool. So we got new stream. Here, which just creates that stream, which does nothing. It's got this reset here, so I imagine they're doing something similar with the caching, and they're going through it and not creating new stuff all the time. They're just creating a pool that all the threads can use, and then making sure it's 0 here. And they fit it out with this reader. So the new stream, they're passing a message.payload, which is a IO reader. IO reader is pretty much just a file. Whenever you use a file, it's pretty much using a reader. So they're passing this payload, which is what's coming over this the wire, and then they're calling decode on it. So the stream has a decode, and this is it doing the exact opposite, because this val can be anything. Reflect type of val, they're doing the same old. Figure out what is actually in there. Info.decoder. So yeah, they're calling the cache type info again and getting the decoder. They're calling decode on the stream. Wait, where's this? Yeah, on the stream. And the value element. If DC error, if that equals OK and the length of decode error context is greater than 0, so they're calling error.decode error, and if it gets no errors and the context is greater than 0, don't know what the context is in this point, they add in the context. So it's really this decoder, and then there was a make decoder, which is, that was when the type cache was built into decoder. In the case of, let's just look at integer again, is uint, there's a decode uint function being passed. Decode uint. Gets the type, wrap stream error if error does not equal nil. Uint type.bits. So it takes the bits, passes them into this uint. Val.set uint as number. Cool. And it's really going to go through everything here. So a string, they're just going through s.bytes. They don't even change anything, they just set the string. Big integers, same deal, bytes, puts it into this big integer value. List decoder. This slice elements. Cool. So RLP is really just a big load of nothing, really. All it does is it takes some elements, saves it with a little bit of information in front of it that only really says the size, and then it also allows for lists. So when you're passing, you're saving all this to the computer memory, or probably to be sent as a message or something. And you just want to be able to pass this whole thing into the computer and it be able to quickly find the information it wants. And it's going to say that this is a list that's this long. Cool, thank you. Copy that into something else. Then it'll read it and go through it and say this is a 3 bytes long, so it'll read this. Cool. And then it'll read the next one. It says it's another 3 bytes. And it's this. And it just does a for loop and it goes for however many items in this. Read this into a string. So it goes cat, done, cool. Next item, read however many this into a string, dog, cool, done. But the key is it doesn't actually say anything about the underlying structure. And it says somewhere here that if you wish to use RLP to encode a dictionary, so you've got some form of key and a value, it's suggested to either use the keys in lexicographical order, or in the case of Ethereum, they just completely avoid using that altogether, and they use these patricia trees, which is a list of hashes, really. And the key is the hash of the data, so if you've just got the data there, you don't need to save the key, and you just go through them, you got the data, and it encodes it. And I think that's where I'll call it today. I might just do a quick look over the yellow paper, because it has a section on recursive length prefix. It's either a list or a byte, I would imagine. Structure T equals list or byte, list equals all the elements 0 to n, and for all n is less than t, and t, n is an element of t. And bytes, yeah. Where 0 is a set of bytes, thus b is a set of all sequences of bytes. So it's all sequences of bytes, otherwise known as byte arrays. L is a set of all tree-like substructures. So this is what I'm saying, it's either a list or a byte, and formally defined in a list and formally defined in a byte. And they look identical. We define the RLP function as 2 sub-functions. When the value is a byte array and when it is further arrays. So it's the list, or if it's a byte. If x is a byte, we do RB. If it's not, it's a list, therefore we do RL. Then they define RB here. If the byte array contains a single byte array that is less than 128, then it is exactly equal to what's input into it, which is them saying it here somewhere. If it's a single byte whose value is that, there. Why am I tabbing that? It's copied exactly out of paper. That byte is its own. Sometimes people blatantly copy out of the formal definitions into a wiki, because wikis are more friendly for people to understand. But this wording is exactly what's in the yellow paper. Same with legislation, to be honest. If you read legislation, sometimes they just copy and paste the legislation onto the web pages. Because people read the web pages, they don't read the legislation. Same with mathematical papers. It contains fewer than 56 bytes. Then the output is equal to the input. Single byte with the value. Prefixed by the byte equal to the length. Yeah, so it's exactly the same as that, pretty much. If it's that, it is prefixed by the minimal length byte array which is interpreted as a big endian integer equal to the length. So they just put, yeah, there. Formally, we define the RB, so the RLP function for the bytes, as if it is x, you put it as x if x is less than 128 bits. Or you do 128, which is 128 is this 80. What is this? 80 is 128. 120? One 26, 7. Oh, I'm looking at oct. Ah, yeah, okay, cool, cool. So the hex 7F80 is 128. That's what I thought it was saying, but I just was looking at it retardedly. So they put 80 plus x, which is the size, so that's the size of x. And then they put x afterwards. So if it's less than 128, they put it itself. If it's more, they put that plus the size and then follow it by that. If it's more than that, they put 183, which is going to be this number here, B7. Clear hex B7, 10, 183. 183 plus the size, and they create a new byte array of the length of the length. The size of the size. And BE is where they define it. It's the sum of, yeah, expands the positive integer into a big endian byte array. They're just emphasizing it's big endian here, not little endian, because everything is in little endian normally. Cool. No, I think that really is everything to do with the RLP function. Not very complicated at all, which is nice. What can I look at tomorrow? Might have a look at ETH database, because they use level database for everything in Ethereum, which is just a key value store, which is quite easy to use. And I don't think they actually do much here. But they wrap it, I imagine. So yeah, they wrap the level database in here. So I might look at that tomorrow. Thanks everyone for tuning in. Appreciate all the support.